In this video, I'll be demonstrating how to implement a generative adversarial network in Google Colaboratory. So the first thing that we need to do is, of course, import the necessary libraries that we'll be using for this program. And after that, we need to make sure that the Google Drive is mounted in this working notebook. But since I already tried this program earlier prior to this recording, it's already mounted. But just to make sure, yeah, we need to double check because later on we will be importing our image in the Google Drive. Another thing that I'm gonna do is to ignore all the warnings, filter warnings, because sometimes there are red herring warnings where they are always appearing even though there's nothing wrong with the program. And another thing that I'll do here is to load or unpack the data. We'll be using the MNIST or MINS data. And to do that, I'll run this part. Okay. After that, we need to check the data that we'll be dealing with. And then, yeah, so here are the data sets that we'll be working on. And now let's define the input image dimensions because we have to take note that larger images take too much time and resources. Here, we only set it as 28 and 28, and then of course the channels 1 because we'll be dealing with black and white images. So yeah, that's the shape of our image. And then after that, we need to build the generator and later on a discriminator. But given the input of noise vector, the generator produces an image. So here in the next block of code that I'll be putting here, we are technically building the model, the generator network with we will be using the dense layers with 3 layers to be specific. And yeah, the generated images will be stored here in the img variable. So let's run that part. And for this part, let's move forward with the discriminator. Here, we will be having a given input image, and of course, the binary classification whether the generated image is real or classified as true or false. But the main goal here is that the generator model will somehow try to fool or trick the discriminator to actually classify the fake generated images into actual or real ones. And here we are done constructing the discriminator and the generator. So for this part, we'll be comparing both models by defining the training function, which is here. And after that, we load the data sets and rescale our training. Convert the float and we'll rescale it to 1 to 1. We can also do a 0 to 1 and of course add the channels dimension. Let's run that part. Okay, so now we'll be needing to create a loop for this one. Let's add some code here. Here will be loop based on the number of epochs, and of course we'll be training the discriminator. Okay, so here here is the remaining code for this block, and then let's run it again. Now that we have the training for the discriminator within the same loop, we will be training the generator, setting the input noise and the training model for it. So I will add the code for the training of the generator. Okay, so this will be a lot of code. but we will discuss each of it. So here we generate a half batch of the fake images. What I'm saying is technically already here. I decided to put it as comment. So it will be a guide for someone who will take a look at the code. So as I was saying, training the generator, here we create noise vectors as input for the model. And then after that, we'll create as many noise vectors as defined by the batch size. For this case, the batch size is 100, and this is based on the normal distribution. And just the same, it will output the same size as the batch size. So the generator wants the discriminator to label the generated samples as valid, and valid samples will be labeled as 1. This is where the generator is trying to trick the discriminator into believing that the generated images is true, hence having the value of 1, multiplied by, of course, the batch size. So here we combined both models, and after that, we'll be needing to track the progress of both. So to do that, we'll be having this part. We'll see the loss and the accuracy of it based on the number of epochs. And so for this part, we'll create another function for save image epochs. And yes, we're done with this block, and then we'll run this. And of course, in building a model, we need to use some optimizer. I'll be using the Adam optimizer, and I will store it in the optimizer variable so we can just easily call it. Okay, so here let me explain this part. Here I set the learning rate and momentum of the optimizer. We can always modify it anytime. And of course, we build and compile the discriminator first. The generator will be trained as part of the combined model later on. Here we use the binary cross entropy as we're going to do some prediction, and it has been found that it is a better loss function as compared to others. So here we finally build and compile the discriminator. Since we're only generating the fake images, let us not track the metrics. And here in GAN, or Generative Adversarial Network, we take noise Z as an input to produce its images. This will have random input to the generator with a size shape of course, 100. And this ensures that when we combine our networks with only the train and train datasets in the generator, and of course we need to check the validity of the generated images, and finally combining both models. So we'll run this part, and we see here the summary of our model. We have a total parameter of 533,505, and same as the trainable parameters. And that's for the first, or the discriminator model. And of course, here's the generator. We have non-trainable parameters of 3,584. And now, to finally train the model, we'll have only, let's say, 5 epochs here. Because again, it's going to take quite some time, and I will save the generator model because I will use it later on in our prediction. Okay, let's run this part and let's see how it's training. We only have an accuracy of 90.62, which is not that bad, but it can be improved with a greater number of epochs. But let's not dwell on that because 90% is good enough. And now, to better test our model, here's an example of generating an image for a specific point in the latent space. So When we're talking about the latent space, it is the compressed representation of an image. Here we load the model that I saved in here. And okay, let's run this part. Okay, so here is the sample of the generated image. It's in black and white, but with greater number of epochs, it will somehow clear out eventually. And of course, let's try loading the generator model once again. And this time, let's generate the latent points. Let's see what will it give us. Okay, so let's add more lines of code in here. And then after that, let's check if it will be plotted. Okay, great. So the generative adversarial network in this program is clearly working, and here we were able to generate a 4x4 grid of images, which is really the main goal of doing a GAN program. And if we check here, the location that I put in where it will be saved, here it is. The generated image from our generative adversarial network. So clearly the program is working. Here's our generated image. Okay, so that will be all. We've reached the 90% accuracy, but it will still improve with greater number of epochs. But again, it's going to take quite some time. That will be all, and thank you.